Yeah, good to go? All right, let's do this. All right, so last talk of the day. It's kind of late. I guess everybody's a little tired. So this talk is going to be a fairly high-level talk. I won't torture you with lots of definitions and theorems and proofs. It's supposed to be high-level, although there are some technical parts. So I'll try to wake everybody up before we get to those parts. Also, I guess the instructions for preparing these talks were that these talks are supposed to be boring to experts. The only issue is that the definition of what?
It's not a requirement.
It's not a requirement. Well, the issue is that the definition for what is an expert wasn't exactly clear. So I hope I kind of aimed this at the right level. Hopefully, it won't be boring for everybody. But if it is, just throw some.
Just make it boring for everybody.
And then I'm guaranteed to be correct. Yeah, I see. So just to make sure it's kind of nice and interactive. So for the experts in the room, if you'd like to jump in and provide more information, just feel free to jump in. This is supposed to be like educational. So the more interaction we have, the better it is for the audience. So yeah, so please jump in, add more color to everything I say. It can only make things better. All right. So with that, let's get started. So I'm going to talk about zero knowledge basically from discrete log-like systems. Whenever I say zero knowledge in this lecture, I'm going to refer to honest, verified zero knowledge, and we'll see why that's the case in just a minute. But before, let's start with sort of kind of the high-level state of the world. So in these last 2 days, you learned a lot about proof systems. I guess yesterday you did PCPs. Today we learned about succinct proofs and methods to achieve zero knowledge and so on. It turns out, as you probably have already seen, there are many, many different paths to succinct proofs, right? We can go the MPC in the head route, as we just heard. We can do the PCP route. Even within the proofs systems-like methods, there are different flavors, whether you open up cells in the proof or whether you answer queries that are inner product queries with the proof. Those are called, basically, those lead to two different types of proof systems. So there are many, many different approaches to building succinct proofs. And the current state of affairs is really, if you kind of look at the different properties of different proof systems, it turns out each approach kind of shines in its own way. And there's kind of no one ring to rule them all, right? There's no Lord of the Ring that has been discovered yet. So I'm hoping one of you can actually do this. So this will be a nice result of this semester-long program. If somebody can actually come up with one method that dominates all methods, and that's the one that we will study and teach and optimize, so we don't have to keep all these 6 different approaches in the head and try to compare them all the time. Okay, so that's your challenge. I hope by the end of this lecture somebody has a proposal for how to do it. But if not by the end of the lecture, maybe by the end of the semester. All right, good. So what I'm going to show you here is yet another approach for providing very short zero-knowledge arguments. I'll explain what transparent means in just a minute. So let's talk about some of the properties of these systems, of these succinct zero-knowledge arguments. So we can compare them along different dimensions. Yeah, so we can talk about the proof size. So often we'd like the proof to be as short as possible. Remember in the blockchain applications, actually I removed all the application slides from my talk because Mutu did a wonderful job. So many of the applications for these systems come from blockchains. In the world of blockchains, the proof kind of goes on the chain. So we'd like to make that proof as short as possible. So obviously proof size is one parameter. How long does it take to produce the proof is another parameter. How long does it take to verify it? Is the proof post-quantum secure or not? And then in this talk, I'm only going to focus on systems that require no trusted setup. And let me explain what I mean by that. Essentially, you don't need to perform any sort of secret ceremony to generate parameters for these proof systems, as is the case for some proof systems. I'm only going to look at systems that require no secret ceremony, so everyone can verify that the proofs are correct, and they don't have to rely on any secrets being kept secret. Okay, so no trusted setup. All right, so with that, those are kind of the parameters, and then the proofs that I want to show you today are called bulletproofs. And by the way, you already know that half the trick in this game is coming up with good names for the systems. So yeah, so Bulletproofs is a kind of a very, very cute name. And so I'm going to show you a system called Bulletproofs. Just so that you see the parameters, if we're trying to prove knowledge of an assignment that satisfies a particular arithmetic circuit, I'm going to let n be the number of multiplication gates in the circuit. So yeah, so the size of the circuit is the number of multiplication gates in that circuit, plus the size of the witness. I'll let that be n. And so the length of the proof is really quite short. Yeah, it's basically 2 log n. It's not even order log n. It's just 2 log n group elements. Every group element is 32 bytes. So you can see that even for very large n, these proofs are going to be like a kilobyte or 2 kilobytes. Yeah, they're actually very short proofs. In fact, they're the shortest proofs that we have.
Binary arithmetic.
What?
Binary arithmetic circuits.
Arithmetic circuits. Yeah, these are arithmetic circuits, and I'm only going to be counting multiplication gates. Yeah. In fact, there are arithmetic circuits over a large field, and I need the field to be large enough so that a group of that order can have a hard discrete log. Yeah, that's where we are. The prover work is going to be proportional to the size of the circuits. Yeah, so it is going to take time to generate these proofs, of course. The one downside is that the verifier's work is also going to be linear in the size of the circuit. So now this was Yuval's comments from the morning. What do we mean by the word succinct? So some people, when they say succinct, they mean a succinct proof. It's a logarithmic size proof, and a succinct verifier, meaning a logarithmic time verification. This is not succinct in that sense. It's succinct in that the proofs are very short, but verification does take linear time. I would actually suggest that we use succinct for short proofs, and we use fast succinct for short proofs plus fast verification. Yeah, that seems to be a descriptive set of words. Yeah, Mutu, you had a comment?
In the batch setting, like the verification would be succinct, like meaning would be better than linear?
In the which setting?
In the batch setting.
Yes, I'll get to that. Yeah, I'll get to that. But right now I'm focusing on one proof. Yeah, so that's a very good point. And then the question is it post-quantum? Well, these systems depend on discrete log being hard, so of course they are not post-quantum, and that's kind of where we are. But they require, as I said, no trusted setup. So one thing that I'll come back to at the end of the talk, because verification is linear time, so verifying is as hard as computing. One thing that you might try to do to alleviate this issue is actually combine this proof system with another proof system that does have fast verification. So for example, I was hoping you would mention Ligero, but never mind. So Starks and Ligeros are basically short proof systems. Yeah, and so they produce short proofs, at least asymptotically, but they're much, much longer than the proofs they will produce here, but they have very fast verifiers. Yeah, so one thing we might try to do is essentially if we want to prove a statement, we can try to prove it using one of these proof systems that is fast to verify, but do generate, in practice, long proofs, and then use bulletproofs to just prove that the verifier accepted the proof. Yeah, so this is a way to maybe combat the fact that these proofs take linear time to verify. I'll come back to this in a bit more detail at the end of the talk. I have to say this is a research problem. We don't know whether in practice this actually makes sense or not. Yeah, so there's kind of practical work to do here to see whether these compositions work. All right, so what I want to show you in this talk actually is go through 2 types of proof systems. The first proof system is due to the ancient Greeks. Yeah, this is why it's a classic proof system, which are called sigma protocols. So sigma protocols the reason they're called sigma protocols is because they're 3-round protocols. So the letter sigma kind of suggests 3 rounds. So that's why they're called sigma protocols. Essentially, there's a message from the prover, there's a random challenge from the verifier, and another message from the prover. Yeah, that's a sigma protocol. What? It should be I was thinking the same thing. It should be a Z protocol, but it's called a sigma protocol. It is what it is.
Since you wanted interaction, I think classic is misspelled.
Ah, yes. Oh, yeah, thank you. Good, I'll fix that later. Yeah, please let that be the type of comments, the type of errors you find. Thank you, Doug. No, good point.
I don't know whether it's a term or just...
No, classic. It's supposed to be the word classic. Yes. Okay. Right. So classic sigma protocols. I guess it's due to when I say ancient Greeks, I mean 1998, and it's due to Kramer and Navgard. I guess not quite Greek, but close enough. And Schumacher too. Yeah, Schumacher too from earlier. Indeed.
Sigma comes from Politani.
Ah, thank you. Oh, yeah, thank you. Say that again.
Okay. Politani was one of official Ronald Kramer's advisor, and Ronald was trying to, he's in algorithms complexity and so forth, but he was trying to explain this thing. Oh, it looks like a C.
Ah, I see. So he didn't, I see. So he should have said C, but sigma is good enough. Okay, so anyhow, with these sigma protocols, kind of the classic proofs of knowledge, essentially the proof size is linear in the size of the circuit. Yeah, so these are not succinct. They're large proofs, and I want to show you how they work. And the modern interpretation of, or the modern version of these Sigma protocols using discrete log, that's what's called bulletproofs. And it's really kind of an exponential compression of the proof size. We go from linear size to logarithmic size. And you wonder, how is this possible? How do we get this massive improvement? And the answer is the proofs themselves require more rounds. So instead of 3 rounds, we go to a logarithmic number of rounds. So that's if you want to view this as an interactive protocol. But all these protocols are just public coin protocols. The only thing the verifier sends is just random junk, random challenges. That's the only thing the verifier does. And Ale in the morning actually explained how protocols that are public coin protocols can be converted into non-interactive protocols by deducing the challenge from a hash function, or more precisely, from a random oracle. Okay, and so in reality, these proofs can be sort of, all these rounds can be compressed into a single round so that the proof becomes non-interactive. So in reality, this actually doesn't matter, but as we think of them as interactive proofs, they're logarithmic rounds. All right, so that's my goal. I want to show you that this is old style, but it's kind of dead. And this is kind of the new style, and that's what people are using now. All right. So let's start. So first of all, what do I mean by proving knowledge of an assignment to a circuit? So let's fix our finite field. So let's call that f. We have an arithmetic circuit that takes n inputs and produces an element in the finite field. Like I said, the size of the circuit is going to be the number of multiplication gates in the circuit. And here you have just one example such circuit. Notice that I also allowed the circuit to use constants, which will just be 1. And the language that we're trying, or the relation we're trying to prove knowledge for, basically says the instance is the circuit, so that's public, what the circuit is. The witness is the assignment beta, and the state, and what we're trying to prove is knowledge of a beta that makes the circuit be true. In this particular case, it means it makes the circuit evaluate to 0. Right? That's kind of the general relation we will work with, and the goal is to provide 0 knowledge arguments for this relation. Yeah. Or actually 0 knowledge arguments of knowledge. And again, as I said, we want to do that in a way that even if we make the protocol non-interactive, there's no need for a trusted setup. So no ceremony to generate parameters that contain secrets. That's our goal. All right. But in fact, I want to do something more general. So these proof systems, these discrete log proof systems, can do more for us than just prove knowledge of a witness. In fact, they interact really well with auxiliary commitments. Okay, so imagine that I also have a bunch of auxiliary commitments to some string gamma. Okay, so gamma is another vector, a vector of length n1, and somehow it just appears in the sky. Yeah, so imagine like on the blockchain, I already have a bunch of commitments to this string, to this vector gamma, and I want to prove properties of this vector. All right, so what is so actually I'll say, the nice thing about these proof systems is they can prove facts about committed values effectively for free. You don't have to do anything to argue that these commitments were constructed correctly. We can directly prove facts about the string gamma. And so more generally, the language we'll be working with, or the relation we'll be working with, is the instance is going to be a bunch of commitments. There'll be some public alpha. You'll see why this alpha is needed in just a minute. Alpha is another vector in the finite field. Here's our circuit that we're trying to prove. And what we want to do, our witness, here, we'll say that basically we're trying to prove that the committed value gamma, the secret witness beta, and this public alpha all satisfy the circuit. Okay, so our witness here is, again, beta is a secret witness, gamma is the committed value, and R is the opening to the commitment. R is just an opening to the commitment. So we're trying to prove these two statements. Is that clear? Everybody with me? So we're trying to prove a joint statement on a secret witness and a committed value that just happens to be available. The commitments just happen to be available to us. So,
what's alpha?
And alpha is some public value. You'll see what alpha is in just a minute. Why we need this. Really, alpha doesn't really need to be there. Alpha could be absorbed into the circuit C, but it's convenient to separate it, and you'll see why in just a second. Okay, good. So in reality, you can imagine we have a bunch of transactions, say, posted on the blockchain. Each transaction maybe has a commitment to a value, and we'd like to prove something about those commitments. Yeah, so that's how these commitments sort of appear out of thin air, because they're produced by somebody else and placed on the blockchain, and we'd like to prove basically properties on these committed values, possibly with another secret beta. So let me show you some example applications that people really care about. And if you can improve the proof systems for these examples, that would be a kind of a big deal. Okay, so let's start So I already said that. So let's start with our first example. So the first type of statement that people want to prove is what's called a range proof. So what is a range proof? Well, we have a commitment to some number gamma. So gamma is an element in our field. And what we'd like to do, actually, we're going to assume this is a high characteristic field. Yeah, it's not a binary field. So we have a commitment to gamma, and what we'd like to do is prove that gamma lies in a certain interval. So you can kind of see that in financial applications on the blockchain in particular, this is kind of a valuable thing to do, where if somebody pays me, they might commit to the amount they pay to me, and they need to prove that the amount they're paying is non-negative. Yeah, that's the main thing we want to do. Prove that the amount that's being paid, that the committed value is non-negative. So that's a typical range proof, and so we want to generally prove that gamma lies in some small interval like this. All right, so how do we do this? How do we convert this into a circuit that we can then verify? Well, what we do is we define another witness, a vector beta, that's going to contain m elements. M, remember, is the number of bits in gamma. So our witness beta is going to contain m elements. And what we need to do is prove that this beta is a bit decomposition of gamma. So what does that mean? So what does that mean? So gamma, first of all, can be written as well, it's a bit decomposition. Yeah, so this basically beta 0 to beta m minus 1 is the binary representation of gamma. That's fact number 1. I'll write this, by the way, as an inner product of the vector of powers of 2 with the vector beta. Yeah, so gamma is equal to this inner product. And second of all the betas are either 0 or 1. That's what it means to be a bit decomposition. All right, so I'd like to prove that this is the case. So you should look at this and you say, wait a minute, this is not what you promised. So you promised that there would be one circuit that evaluates to 0. Right? That's what we need to do, to check. One circuit evaluates to 0. But here you have m equalities over here and another equality over here. Here you have m plus 1 equalities that we're trying to check. It's not one equality, it's m plus 1 equalities. So what do? If we have m plus 1 equalities and we want to convert them into a single equality, what do we do? What? And. Well, and is not an algebraic operation. We're over a finite field. We're dealing with arithmetic circuits. We can only do algebraic operations. So multiply them all. Well, multiplication doesn't quite work. If you multiply them all, that's an OR. Square and add. Okay, that's interesting. Let's just start with add. Let's suppose we add them all up. Yeah, suppose we add them all up. And we ask, is the sum 0? Does that work? Add them all up and ask, is the sum 0? Does that sound?
Maybe negative, maybe positive.
Yeah, I mean, imagine one of them is -5 and the other one is 5, right? Then they'll sum up to 0, but it doesn't mean that they're both 0. So that doesn't work. So what else do we do? How do we combine a bunch of equalities into one equality? We can't just add them up. That's insecure. What else do we do? It is an arithmetic circuit. Our absolute value is not an arithmetic operation. No, polynomials. Ooh, somebody said polynomials. That's a brilliant idea, actually. Generally, by the way, in this field, whenever you have a problem, the answer usually is polynomials. Just keep that in mind. That's usually what happens. Okay, so what are we going to do? What we'll do is we're going to combine all these into one relation in the following way. This is where alpha comes in. Okay, so we're going to take we're going to have a random public value alpha. And now let's look at what we do here. So I take the first relation. So gamma minus this inner product, that should be equal to 0. And I'm going to leave it as is. Okay, now I'm going to add it to the second relation, but I'm going to multiply by alpha. Okay, I'm going to add the third relation. I'm going to add all the way up to the end, and I'm going to multiply each one of the relations by a power of alpha. Right? So essentially, I took all my relations, and I multiplied the ith one by a power of alpha to the I. Now, why does that work? Why does that work? Let's suppose that, in fact, this circuit does a value to 0. So let's imagine for a minute that this crazy thing, this crazy expression actually does a value to 0. I claim if that's true for a random alpha, that means all of these relations, all of these coefficients essentially must be 0. Well, why is that true? Let's just walk through the argument. This is a general technique that comes up all over the place. So I want to walk through it one time so everybody understands this. Yeah, so what we have here is essentially a polynomial in alpha, polynomial degree m minus 1 in alpha, where the relations are the coefficients. All right, and what we're doing is we're evaluating this polynomial at a random point alpha. If this polynomial evaluates to 0 at a random point, Well, a polynomial of degree m can have at most m roots. We evaluated, our field is gigantic, right? It's Q point. We evaluated at a random point and we got 0. That means the polynomial must be the 0 polynomial. Yeah, so if this circuit evaluates to 0 at a random point, the polynomial must be the 0 polynomial, which means that all the coefficients must be 0.
So if you just ask the question, if you take the alpha to be the size of the field, then...
Alpha is a scalar. Alpha is a value in the field. Alpha is like 5, 7, 19, 31.
What is the size of f? If you take the
F is going to be huge. F is going to be like a 200-bit number. So F is huge. F is much, much, much bigger than M. Yeah, so the only reason I went through this slowly is to say that the way you combine a bunch of relations is literally by selecting one random alpha and combining things in this way and checking that the result is 0. Yeah?
Are you choosing alpha here like as the output of a random oracle or something?
Ah, excellent. Excellent question. Amit usually predicts where I'm going to go next. So we kind of explained why this actually works. The question is, where is this alpha coming from? So can the prover choose alpha? Well, no, because if the prover got to choose alpha, he would just choose an alpha that's a root of this polynomial, and then we'll get 0 even though it's not supposed to be a 0. It's kind of like the problem that Ali had in the morning. So really, where we would like this alpha to come from is from the verifier. Yeah, so effectively what we'll do is we'll make the prover commit to all the coefficients. Then the verifier will produce alpha, and then the prover will prove that the circuit evaluates to 0. Yeah, that's kind of the general techniques. And of course, like Amit was saying, if we want to get rid of interaction, we can derive alpha from a random oracle. Right? So is that clear? This is just a general technique, very cute trick for combining a bunch of equalities into one using just one single random value from the verifier. Yeah?
Why not use random linear combination? Why is choosing more random?
Great. Yeah. So Muthu actually has exactly the right point, which is to say, we could have just taken a random linear combination of these relations. We didn't have to go through crazy polynomials. The problem with the random linear combination is now we would have to have the verifier send an entire vector.
You can always do PRGs to expand.
For sure. But now you have to start using, eventually you're going to have to prove that the PRG was evaluated correctly. This is much simpler. You just send one value and it's all arithmetic. That's very, very easy to prove.
Prover anyway sends a long message because he has commitment, so he has to read that much, no? That doesn't matter?
Well, but it reduces the. So again, we're going to make all these things be non-interactive. So eventually, the prover is going to derive these things from a random oracle. So it's more efficient to basically use the random oracle, kind of a short random oracle, to produce one alpha rather than to use it to produce like a long string. It's an efficiency issue. You're absolutely right. We could have used a random linear combination. It's just more efficient to just do it with a single element.
It's efficient in the randomness.
Exactly. Efficient. Exactly right. Yeah. That's exactly right.
Even for the active version, it's more efficient.
Well, in the interactive version, it's definitely more efficient because you send less data. Unless you use PRGs, but then you have to prove that the PRG was evaluated correctly. So that would be a mess.
Expensive with the random oracle.
It's what?
You can expand it with a random oracle anyways, but
Only if you're in the non-interactive settings. Yeah. So okay, I think we understand what. So let's move on. So that's example number 1. Now, so example number 1 is, like I said, range proof. This is actually where these proofs are actually used in practice. So many of the blockchains that deal with privacy now basically work by having the people who spend money, they commit to the amounts that they're spending. And like I said, you have to prove that those amounts are positive. And so these proofs are actually proving this statement is what's used in practice. The classical Kremen-Daugard method, or I'll say the classical Greek method, would have required linear proofs that are linear in M, linear size in M. These new methods, the proof size is logarithmic in M. Yeah, logarithmic in M. So it's a huge improvement over what's been done before, and I'm going to show you how this works. So that's one example application. The second example application I want to show you is what's called a polynomial commitment. So polynomial commitment is a term you're going to hear a lot about throughout this program, throughout the semester. So let me explain what a polynomial commitment is. So in a polynomial commitment, we basically commit to the coefficients of a polynomial. This is a polynomial of degree n-1. So we commit to the coefficients of the polynomial, and we give you 2 more values in the clear. So alpha 1 and alpha 2. And your goal is basically to prove that if I evaluate the polynomial at the point alpha 1, I get alpha 2. Yeah, that's the statement we want to do. So I commit to a polynomial, and then later on I can open up the polynomial at any point, and I should be able to convince you that the value is what I claim it is. That's what a polynomial commitment is. Okay, great. So how do we do it? Well, the circuit is very simple. We just want to argue that this circuit is equal to 0. You know, output's 0. I guess here there's no beta even. There's no secret witness. It's all, there's the points alpha and then the secret gamma, the committed gamma, and we just need to prove that this evaluates to 0. So that's a polynomial commitment. Now, ideally, what we'd like to do is we'd like to have short proofs. Yeah, so the proofs need to be logarithmic in the size of the polynomial in the degree, and we'd like to have fast verification. And in fact, there's an old paper by Kate, Kate et al. That it's pronounced Kate. Yes. Is everybody happy with that? Yes. Is he here? No, he's not here. Okay, by Kate et al. From 2010 that shows how to do this using bilinear maps. Yeah, so we have actually proofs that already satisfy this very, very elegantly. Short commitments, short proofs, and fast verification. The only problem is this requires a trusted setup. This requires what's called a structured reference string. So it does require a trusted setup. We'd like to do everything without a trusted setup. And so the answer is we can do that. We can do this without a trusted setup using what I'm about to show you. However, remember, verification for us is linear time. So the property that we don't achieve is logarithmic time verification. Our verification will be linear time. Somebody had a question.
Was the proof size in that paper not constant even? Or?
It's a one group element, yeah. Oh, did I say logarithmic? Yeah, the proof size was 1. No, I said that's the goal. They achieve even, they outdo themselves. They achieve even better. Right, they achieve even one group element for the whole proof. Yeah, so by the way, I should say, if somebody can improve these polynomial commitments, that would actually be pretty cool. Yeah, because that's useful in the sonic proof system and in many, many other proof systems. So that would be pretty cool. All right, so that's example 2. The third example application I want to tell you about is another cute application, which is a verifiable shuffle. Yeah, so what's a verifiable shuffle? Here I have a commitment to 2 vectors. Yeah, so I have a bunch of numbers and a bunch of other numbers. Yeah, these are vectors of length n, and I want to prove that one vector is a permutation of the other. So these are useful in mixed nets. They're useful in voting systems. In fact, this is where these schemes come from, originally from proving that mixing of votes worked correctly. So the question is, what's the circuit to prove a shuffle? And so let me show you. Actually, maybe somebody has an idea. How do you prove? Can you give me a circuit that verifies that one vector is a permutation of the other?
Polynomials.
Polynomials, yes. Very good. Learning fast. Excellent. Yeah, so here's what we do. So again, what we'll do is we'll choose a random alpha, and what we'll effectively do is we'll define a polynomial that has the first set of inputs, the gamma 1 inputs, as its roots. Okay, so it's a polynomial where gamma 1, 0, gamma 1, 1, gamma 1, 2 are the roots. And we're going to evaluate this polynomial at the point alpha. And then we're going to define another polynomial that has the second gamma as its roots. And if one is a permutation of the other, you realize these 2 polynomials are identical, right? If one vector has gamma 1 as its roots and one polynomial has gamma 2 as its roots, and one is a permutation of the other, those 2 polynomials must be the same. So when we evaluate it at a random point, they must be equal to one another. And if they are equal to one another, then with very high probability, these polynomials are equal, and we have a proof of a shuffle. It's a cute trick. And so the question basically is, how do we come up with a short proof for this shuffle? And again, the answer is using these new techniques, we can get a proof whose size is log n. Log n. So you have a commitment to n elements, and we can prove that it's a shuffle using log n group elements. All right, so that's kind of the goals. That's where we're headed. And so let's do it. All right, so let's do it. So the first thing I want to do is actually move away from circuits. Yeah, so it turns out circuits are not that convenient to work with when we talk about these proof systems. There's a much more elegant language to talk about, to use in these proof systems called rank 1 constraint systems, due to Ali and others. Here's my definition of it. Essentially what we'll do is the computing model is we're going to fix a bunch of matrices, A, B, and C. So instead of giving you a circuit, I'm just going to give you matrices A, B, and C. And what I want you to prove to me is that there's a vector x where the first element is 1. This is the scalar that we allow you to use inside of the circuit. The last element is 0. This element is going to represent the output of the circuit. Okay, so this proves that the circuit evaluates to 0 at the witness. And it so happens that, well, there's a certain relation that's being satisfied. So let me explain what this relation says. This circle here means component-wise product. Okay, so we multiply the first element by the first element and test that that's equal to the first element. Second element by the second element, test that it's equal to the second element. Okay, so there are, what is it? There are m equality relations being tested here. All right, that's kind of the version of R1CS that I want to work with. And it's actually quite easy to see that any circuit, for example, this circuit, can be represented as R1CS. Let's just walk through it very quickly. What we'll do is we'll take our witness, x1, x2. So here's the input, x1, x2, and 1, I guess. We'll put the witness at the beginning, all right? And then we're going to expand our input using all the outputs from all the multiplication gates. All right, so you can see W1 is the output of one multiplication gate, and W2 is the output of the other multiplication gate. Right, so we add the outputs of multiplication gates to our witness. And you notice, of course, the last element is the actual output of the circuit. And then you can pretty much see what the matrices are going to enforce. The matrices will enforce that all the multiplications are done correctly. All right, so let's see. So we have, you can look sort of at the rows here. So you can see that x1 times x2 is equal to w1. That's this gate. x1 times x2 is equal to w1. You can see that w1 times x2 plus 1 is equal to w2. Yeah, that's this gate. And so on and so forth. Yeah, so we can encode all the multiplication gates by these matrices, and that's basically how we encode a circuit as 3 matrices. So you're going to be hearing the term R1CS actually again throughout the semester. So it'd be good for you to just know what R1CS is, and it's just convenient for us to kind of work with it when we do proofs on arithmetic circuits. All right, so the number of multiplication gates is what we call the number of constraints, or really what it is just m, the number of rows in the matrices. And the number of columns is basically the number of inputs plus the number of multiplication gates. Okay, so that's R1CS. But in fact, we actually want to work with R1CS with auxiliary commitments. Yeah, so in fact, we're going to expand the relation to take in our A, B, and C, but also take in additional commitments on the outside. Okay, and we're proving statements about the witness gamma and the committed value gamma and some witness beta. All right, so this is the statement that we're actually going to prove. So far so good? So this might be a little confusing. This is a little bit of a definitional, mechanical. There's nothing interesting here. It's just a mechanical step in the talk, just so that you see what kind of languages we're going to be working with. Yeah?
So this constraint system will only specify multiplications, right? Or not?
Well, the circuit is addition and multiplications. Yeah? We only care about multiplication gates because additions, we can, as you'll see, additions are for free. Yeah, so multiplications is where all the work has to be done. All right, so we're going to be building a proof system that handles witnesses that are partly secret and partly committed. That's what's happening here.
So what's W there?
Oh yeah, yeah. Oh W. Oh yeah. Thank you. Yes, and W is basically these wires. W is the outputs of all the multiplication gates. Yeah, so we extend our witness. We take our witness and we extend it with all the outputs of the multiplication gates, and that's what allows us to write it like this. All right, so it's kind of cool. We can summarize an entire circuit using 3 matrices and 1 multiplication condition, and that's it. Any questions on this?
How are you checking the addition in the circuit? I think I missed that.
Okay. Well, so what we'll do in the circuit is we'll just literally use the matrices to compute the additions for us. So let's look at a particular multiplication gate. The inputs to the multiplication gates, because the circuit only has multiplication and addition gates, the inputs to the multiplication gates must be themselves linear functions of previous multiplication gates. And that's it, right? They must be linear functions of previous multiplication gates. So you can see here, the input is x2 plus 1, and so our matrix computes x2 plus 1. Yeah, so all the linear gates we can absorb into the matrices, and the multiplication gates are being verified by the rank 1 program. Yeah, that's it. It's pretty cute, actually. It's very convenient. So thank you, Ali, for doing this. This is very convenient to work with, and it's kind of cute. Okay, very good. So we're making good progress. So let's look at our first proof systems. So the first thing I want to do is, again, show you kind of the classical Sigma protocols And let's see kind of how they work and why there's zero knowledge and so on. All right, so the first thing I have to do is introduce kind of the basic building block, which is what's called an additive homomorphic commitment. Yeah, so what's an additive homomorphic commitment? Well, what I'll do is let's fix a particular group of prime order Q, and let G and H be independent generators of this group. Now, there are two additively homomorphic commitments. So the first one, which I'll call option 2, is actually the simpler one, which says the following. If I want to commit to a field element, so these are scalars, commit to a field element using randomness R, what I'll do is I'll just compute g to the gamma times h to the r. That's our commitment to gamma. This is called a Pedersen commitment. And you can show this commitment is actually information theoretically hiding. That should be easy to see because h to the r completely, it's like a one-time pad that's being applied to g to the gamma. So this is just an independent, it's a random element in the group independent of gamma. So it's unconditionally hiding, but it's computationally binding. Computational depending on the fact that the discrete log of h base g is unknown. So it's computationally binding if you're in a group that has a hard discrete log. So by the way, if you have a quantum computer, this commitment will break. It will be insecure because you'll be able to compute discrete log and open the commitment in ways that you were not supposed to. Because it's only computationally binding and the prover is going to commit to us, this is why we end up with an argument, not an actual proof. Yeah, we have to assume the prover cannot break discrete log. So that's a Pedersen commitment. And the other option is an El-Gamal commitment. An El-Gamal commitment is basically an El-Gamal encryption of gamma. And this commitment is basically the other way around. Yeah, so it's unconditionally binding. You can see that basically this term defines what R is. And once you know what R is, you can solve for gamma. Yeah, so this is actually information theoretically constrains what gamma is, so it's unconditionally binding. If we use this type of commitment, we'll get an actual proof. Doesn't matter how smart the prover is, he will never be able to fool us because he can't open the commitment in a way that he isn't supposed to. But in this talk, actually, I'm going to focus just on these computationally binding commitments because, as you'll see, they actually give us what we want. This is why everything we get is just arguments. We don't get actual proofs. All right, so why did I talk about these commitments? Why did I define these commitments? Oh, sorry, one more thing is if I need to commit to a vector, I'll just commit to an element of the vector one at a time. So far, so good? So we know what computationally hiding, we know what homomorphic commitments are, and we know how to commit to vectors. Why did I call them homomorphic commitments? Well, it's because they have additive properties. Again, I imagine many of you have already seen this. So if I commit to gamma 1 and gamma 2, it's supposed to be gamma 2, I can compute the sum of the two. I can compute a commitment to the sum, basically by multiplying the two commitments together. Yeah, so I can compute to the sum. If I give you a commitment to gamma in a scalar, I can compute a commitment to A times gamma. And if you combine these two together, what it means is if I give you a commitment to a vector and a matrix, then I can compute a commitment to A times gamma. Okay, that's what the linear homomorphic properties let us do. So I imagine many of you have seen this. Are there any questions on this, or is that clear? Yeah, everybody's good? We're going to use these properties now over and over and over. Okay, so let's see how the proof system works. So remember, we have our instance, which is a bunch of commitments, C. We have our matrices A, B, and C. We have our witness. Our witness, remember, contains this beta, gamma, and the wires, plus the witness contains the opening to the public commitment. What we want to prove is that AX times BX is equal to CX. That's the R1CS condition. We want to prove that we know that gamma really is what's being committed to in a public commitment. And we want to prove that the final output of the circuit is equal to 0. I'm going to call that condition star. That's what it is. That's what the proof is trying to prove for us. All right, so the way we do this classically, again, the prover has the instance in the witness. The verifier only has the instance. The way the classic commitments work is actually very, very natural in that what we do is we basically send a commitment to this vector x. Yeah, this is our witness. Yeah, we send a commitment to the witness. And now if you think about what we have to do, basically we just have to prove, we send a commitment to the witness, but we don't have to commit to gamma because we already have a commitment to gamma. Okay, so we can exclude those commitments from the thing we send to the verifier. And we just use the public commitments. This is why these systems kind of work organically on top of commitments. And so we send a commitment to the witness over to the verifier, and then the only thing we have to do is just using the linear homomorphic properties, both of them will compute commitments to AX, BX, and CX. And then they're going to prove that condition star holds on these commitments, that this condition holds on the commitments. That's it. That's the whole proof. Okay, so of course, somebody should ask me, how do you do this?
How do you do that?
That's an excellent question. Thank you. Yes. So so how do you prove that these conditions actually hold? And for that, actually, if you just think about this for a minute, you'll see that these are this reduces down to fairly basic statements. So what it is we're trying to verify? We're trying to verify that the first component of this commitment times the first component of this commitment is equal to the first component of this commitment, and so on and so forth. Abstractly, this means if I give you a commitment to A, a commitment to B, and a commitment to C, you want to prove that A times B is equal to C. All right? And for that, it turns out there are very simple zero-knowledge proofs. Yeah, just to prove, given 3 commitments, to prove that they satisfy this multiplicative property, it's a very simple zero-knowledge proof, and so this takes care of the first part. The second part, just proving that I have an opening to a commitment, this turns out to be a proof of discrete log. Again, very, very simple proof. We know how to do this very well. And to prove that this is 0, all I do is I just open the commitment. And I show you that it's a commitment to 0. All right? So I was going to show you actually how these actual proofs work. They basically use sort of this generalized Schnorr protocol. But I think in the interest of time, I'm going to skip over this. There's other more interesting things I want to show you. So let me actually skip over this. And I'll just tell you that at the end of the day, with these classic proofs, you remember we had to commit to our witness, and then we had to prove facts about our witness. Just commitment to the witness, just by committing to the witness, we already lost. Right? So because when we commit to a vector, we commit to the vector component by component. Right? So if we have an n-long vector, we'll end up with n commitments. So already we have a huge proof. And then proving condition star, again, gives us a linear size proof. So we've already lost just by step number 1. Step number 2 makes us lose even more. Yeah, so these are kind of the long proofs that we want to avoid. Okay, so the question is, what do we do? What do we do? And so this is how we go from Sigma protocols to these bulletproofs. Let me show you what the trick is. How do we shrink, how do we avoid this step 1? Somehow we have to improve our commitment scheme so we can shrink everything and make the proof much, much shorter. So first of all, I should say that Bulletproofs is due to Budel et al. And then to Bunz and Budel et al. Benedict is sitting right over there. Is Jonathan here? No. Yeah, there you are. Thank you. Yes. It's funny to talk about you guys when you're here, but that's good. So so this is captured in 2 papers and as well as some follow-on work. So let me explain how this works. So what was the problem with the classical scheme? In the classical scheme, again, if we wanted to commit to a vector, we had to commit 1 element at a time. So we got a linear size commitment. And that already made our proof be linear size. So the idea to improve that is to improve our commitments. Yeah? So we're going to use what's called a multi-commitment. And in a multi-commitment, I can commit to an entire vector using a single group element. Okay, so let me explain how this works. This is the old commitment, right? So when we commit to 1 element at a time, and as a result, we end up with a linear size commitment. In a multi-commitment, what happens is the following. We have a bunch of independent group generators. Yeah, so nobody knows any discrete log relation between these group generators. And by the way, these are, because they're random, there's no trusted setup here. They could all just come from a setup procedure. In particular, they could be generated by a random oracle. That's fine. And the way we commit to a vector is basically by producing this multi-commitment here. So we just do G1 to the alpha 1, G2 to the alpha 2, G3 to the alpha 3, and then we blind by H to the R. So you see that a single group element is committing to an entire vector. All right? These proofs are computationally binding, assuming discrete log in the group is hard. But the cool thing is, again, we kind of solve our problem in that a single group element commits to the entire witness in one go. All right, so that's step number one. We have this multi-commitment.
So the GIs are generated by random oracle.
Yeah. So if we had to generate them, if we somehow had to give the verifier these generators, the proof would be too big. If we had to generate them by a trusted setup, well, that would require a trusted setup. But they're just random elements in the group, and so we can just generate them arbitrarily.
It doesn't know anything about them. So it's
Exactly. As long as there's no known discrete log relation. So that's critical. Yeah.
That's what these days other people call a Peterson hash function. Is that?
Yeah. So Peterson it's fine. That's correct. Yes. Actually, sorry. Let me take that back a minute. That's not quite correct. So there's one small difference in that the reason I call it a commitment or a multi-commitment is because I blind. A Peterson hash would not have the blinding here. Yeah? Okay, good. So if we take this away, then it's a Peterson hash.
Yeah.
Perfect. All right, good. Yes, please.
The generator still is something that the committer and the receiver need to have in its head. So in terms of space, I still have to keep that much amount of space.
Not only do you have to keep this amount of space, actually when you generate a proof, you have to evaluate the random oracle to generate all these generators. So this is why you have to spend linear work to produce the proof and linear work to verify the proof. You have to produce the generators. Step number one. There are other reasons why it's linear, but this is one reason, for sure. It's linear work, linear space. But the commitment is only a single group element. Okay, cool. But we're not done. Sorry. So just for simplicity, what I'll do is just to introduce some notation. I'll say a vector of g's raised to the vector of alphas means this. All right, so this will just simplify what's coming. Okay, good. Everybody okay with this? So that's the Peterson hash. G to the alpha is a hash of alpha using base G. All right, so now the question is, if we have a multi-commitment to a vector, what can we prove about this vector? That's the problem. Yeah, that's kind of the question we have to solve. So just compressing the commitment by itself is not enough. We have to prove that star, property star, holds for this multi-commitment. So how do we prove properties on a committed vector? And it turns out here, the problem really just boils down to one thing. Yeah, the core of the bulletproof system is basically a non-zero knowledge argument. It's succinct, but it's a non-zero knowledge argument for what's called an inner product proof. So what is an inner product proof? Now, please pay attention here. This gets a little bit tricky. But if you understand this, you understand bulletproofs. So let me see if I can get this across in 5 minutes. All right, let's see. So again, what is the statement we're trying to prove? So we have a vector of actually two vectors of generators. We have another generator V, and then we have another element P. The statement we're trying to prove is that if I give you the element P, the prover knows vectors alpha and beta such that, if I compute the Peterson hash of alpha times the Peterson hash of beta, and I multiply by their inner product, then I get the element P. Okay? That's the whole statement we're trying to prove. That's the core of the bulletproof proof systems, is just proving this type of statement. I know vectors alpha and beta that satisfy this relation. You can see why it's called an inner product proof, because I'm proving knowledge of a commitment to two vectors and their inner product. All right? Now, remember, this P is a single element. It's kind of remarkable. It's a single group element that captures two huge vectors and their inner product. Yeah, and we just need to prove the inner product statement. Everybody with me? Okay, so let's do it. Now, this is kind of a cute proof. So, yes, please.
Given here as part of the statement, or it's implicit in the witness?
Alpha and beta are the witness.
Yeah, but the result of the inner product is given, or?
No, nothing is given. No, nothing is given. Everything is absorbed into this element P. The only thing that's given are these things.
Oh, it's implicitly defined by the vector.
Yeah, given the witness alpha and beta, the inner product is defined, and we're multiplying by V to the inner product. Yeah, this is the only thing that's given. This is a statement, and alpha and beta are the witness. That's it. Yeah?
V is provided by the prover. It's not you from the trusted source or something.
Actually, these elements, G, H, and V, they're going to come from the random oracle. P is going to be provided by the prover. P is the proof, yeah. Actually, P is the instance. P is the statement that we're trying to prove.
Oh.
Yeah. Yeah.
G and H are generated for each proof. The G and H.
No. G and H are fixed forever. Yeah, these are fixed generators forever. Really, the only thing that changes is P.
So how did you create these G and H?
They came from a random oracle. Yeah, just evaluate the oracle at 1, 2, 3, 4, 5, and that gives you the generators.
They're not quite the multi-commitments, right? Because
No, they're not. This is not. Well, no. You could view this as a multi-commitment. Well, there's no blinding. So this is a hash. Really, in fact, I'm going to think of this thing as a hash function in just a minute. Right. So we want to prove that if you think of this whole operation as a hash function, we want to prove that we know a pre-image of this hash value, where the hash value is p. All right. That's the core of the proof. Now, let me show you how this proof works because it's pretty cute, and then hopefully it'll be clear. All right. So the proof that I'm going to show you has literally just 2 log n elements. This is where the compression comes from. Yeah, please.
Is it like a proof of knowledge? Is that what the point is? It's always going to be true, right? Or something like that?
Yeah, it's a proof of knowledge, exactly. It's not. But the point is, it's short. It's short. Yes, it's an argument of knowledge. The point is, it needs to be a short argument of knowledge. Yeah, that's a good point.
The question was like because all these always exist, right? There are always.
Absolutely. Yeah, exactly. So you want to prove that you know it. In fact, we're going to have to build an extractor. Yeah, that extracts it from the prover. But the point is, the proof itself is very short. You could always just send the vectors alpha and beta in the clear. If we don't care about zero knowledge, just send alpha and beta, but that would be a long proof. Our goal is to build a short proof.
So the
Yeah.
prover sends the verifier, if I want to think about people sending to each other, this P.
No, you shouldn't think of it like that. Think of it as the instances, the verifier basically has this P. Actually, both the verifier and the prover has this P. This P will fall out of the statement that they're trying to prove, out of the circuit they're trying to satisfy. So they both have P. And now the prover wants to convince the verifier that it has this witness alpha and beta, satisfying this condition. Yeah. And it has to do it, that it knows this alpha and beta, so we have to be able to extract this alpha and beta. And it has to do it with very, very few group elements.
And P is the assignment to the wires.
P actually, because this is not going to be a zero knowledge proof, this is it's a sound proof, but it's not zero knowledge. This P is going to be derived from the assignment of the witness and the assignment of the wires, but everything is going to have to go through some blinding process to make it zero knowledge. Yeah, but for now we're just going to focus on this statement and not worry about zero knowledge, just worry about succinctness. All right? So far so good? Please ask any other questions? I want to make sure what it is we're trying to prove should be clear.
It's not, you don't care about zero knowledge, but isn't just send an alpha and beta.
Yeah, so you could send alpha and beta, just send the vectors alpha and beta in the clear, but that would be a linear size proof. Our goal is to build a logarithmic size proof. Yeah, that's it. Cool. So we're focusing on succinctness, succinctness and soundness, not on zero knowledge. Okay, so let me show you how to do it. So this is going to be interesting. Yeah, let's see if I can do this in 2 minutes. Yeah, so as we said, we're going to define this. Let's define this hash function. So I'll call it a hash function based on g, h, and v of alpha and beta. This hash function is literally going to be defined as a thing that outputs this value. Okay, this is just a notational convenience. So if I hash alpha and beta, I get this particular group element. It's a single group element. So that's what the verifier has P, and the prover wants to prove that it has a pre-image of this hash function. Well, so the minute you see a logarithm in the proof, in the proof size, you already know how the proof is going to work. Right? The proof is going to be some recursive procedure. So if we're going to recurse, what that means is we have to break our statement into 2 halves. Okay, so how do we break it into 2 halves? Well, let's think of the left side of alpha and the right side of alpha, and the same thing for beta. All right, so that's so far I didn't do anything. All I did is I just said let's break alpha into alpha R, alpha L, and alpha R. Now, let's try a straw man proposal first. Imagine that we compute. Oh, by the way, we can do the same thing to G, right? So we can break it into the left half and the right half. So let's imagine that the prover sends this hash value PL to the verifier. So this means GL to the alpha L times HL to the beta L times V to the power of their inner product. So suppose we send PL to the verifier, and we send PR to the verifier as well. Can someone tell me what's the relation between P, PL, and PR? What?
Product of it.
Thank you. Yeah, exactly. P is equal to PL times PR. So what the verifier wants to check, the verifier can just check that this product verifies. And now they need to recurse and prove that PL and PR satisfy the same relations. But this doesn't work, right? Because if you recurse twice, that's going to give us a binary tree of linear size. So we didn't compress anything. So somehow the way all these proofs always work, this is by the way, whenever you design a proof system, the first thing you should try to do is break your problem in 2 halves. show that you can break it into two subproblems, but you can't recurse on both subproblems. What you have to do is take the two subproblems and combine them into a single subproblem, and then recurse on the single subproblem. That's what we'd like to do. So the question is, how do we combine PL and PR into a single subproblem? So this is not so easy, actually. This is not so easy. So I'll just tell you, there's a lemma here that shows how to do it. So let me see if I can explain what the lemma says. All right, so we have our P that's defined using the combined vectors. And the way we're going to and then we have some X. X is like a challenge from the verifier. The way we're going to combine the two halves into a single instance that's half the size is in this weird way. Yeah, we compute, X times alpha L, X inverse times alpha R. Same thing on beta. And then we do the same thing to the generators. Okay, so we have, so you notice this is half the dimension, this is half the dimension, and the generators are half the dimension. Right? Oh, yeah, so here. These are half the dimension. And so what we'd like to do now is basically have the verifier compute the subproblem, right? Compute the subproblem, and then we can recurse on this subproblem. The problem is that the verifier can't give the verifier, given the values that it has, it can't actually compute this value. This hash value, we don't know how to derive it from the values that we have. So what we have to do is give the verifier enough information to compute this new hash. And this new information are these quantities L and R. You can think of them as sort of cross products. You can see GR is paired with alpha R, alpha L, and HL is paired with beta R. Yeah, so these are sort of cross product terms that naturally come from an inner product. And now, lo and behold, given L and R, it's actually easy for the verifier to compute the new hash value. Yeah, this is a lemma. So this you just have to trust me. It takes 30 seconds to prove, but you have to trust me that this is correct. Okay? So given L and R, the verifier can compute this new value, which we're going to call P prime. And lo and behold, now we have a problem that's half the size of the original problem, and we can recurse. Right? Now we just need to prove that the prover has a pre-image of P prime. That's the whole idea of bulletproofs. By the way, this is the whole idea of any recursive type proof system. So just remember this as a hint. Every time you want to come up with a succinct proof, you try to break your problem into two halves, combine the two halves, and recurse on the combined problem. And that gives you a logarithmic size proof in logarithmic many rounds. Okay, so now that we understand that, so you can see how the proof is going to work. The prover sends L and R, the verifier sends X, and then they're going to, and then in one step, the prover at this point can output alpha prime and beta prime, and the verifier can check that those values are correct. And already you see we're making progress because these values are half the size of the original value. So originally, the dumb protocol would require the prover to send two vectors of length n. Now the prover is sending two vectors of length n over 2. So we're already making progress. And of course, we're going to recurse. So things are going to get only better. Yeah?
Very nice. But
yeah.
You didn't convince me of anything. So why is this particular instance that you chose, what is the probability of error here?
No, absolutely right. So I didn't convince you of anything. Indeed, we're not done. So in fact, thank you for asking the question, because all I want to do at this time is just put up this bubble. And the bubble says that if you look at this one-step protocol, this is an argument of knowledge. In fact, what you can do from it is you can either extract alpha and beta from the prover. So remember, he sent us alpha prime and beta prime. If you rewind and do all the standard proof system voodoo, you get alpha and beta. However, there's a failure probability. There's a failure event. You might fail to get alpha and beta, but if you fail to get alpha and beta, you'll get discrete log relations. This second line is why this is an argument and not a proof. Yeah, we're not actually proving knowledge because we might fail, but if we fail, we produce discrete log values. So if discrete log is hard, we must be getting this quantity.
So can you remove the bubble from
Yeah.
So what would be the other query that?
Oh, you would rewind and just send different x's.
And that's not?
Well, 4. You need 4 x's. With 4 x's, you can recover alpha. Yeah. Yep. So that's the proof of security. Yeah. So actually, walking through the proof takes a bit of work. So I'm not going to do that now. You can ask me after if you want to see how this works. Okay, we're almost done. So now you can pretty much see how the proof is how the inner product argument is going to go. We're going to do this once. We're going to do this again and again and again. We're going to do this log n rounds. At the end, at the end, now the the prover at the end just has two values, alpha and beta. These are scalars now. So it just sends the scalars over to the verifier, and the verifier actually checks that the alpha and beta are correct. Actually, what the verifier does is it computes pk, the generators, and the final value p, and it checks that everything is consistent. Okay, that's the proof. That's the core. That's the inner product argument. Yeah. So far, so good. This is just to give you a taste, the idea for how this works.
Nice cryptographer. What would happen if you, when you have the two sides, you continue, you just randomly
choose one of them? Yeah, that's a very good question. So like you suppose instead of combining the two halves together, we just recurse on one of the sides and ignore the other one. The problem is then the soundness is actually quite bad. The soundness will only be 1/2 because the attacker might, a malicious prover might only get one of the sides right and the other side would be not right. So now we'll have soundness 1/2 and we'll have to repeat the proof 100 times. If we repeat the proof 100 times, the proof blows up by a factor of 100. Yeah, so actually low soundness is a problem for us. We want to get negligible soundness. It's a good question. All right, so maybe I'll skip over this. Actually, no, I'm not going to skip over this. This is kind of important. If you unwind the recursion of the verifier, something really cute pops up. Yeah, if you unwind, you actually ask, what is the verifier actually doing? It turns out the verifier actually is producing these challenges, these log n challenges. From these challenges, it's actually, in a very cute way, it's producing this linear size vector. And then it's just computing these two linear size exponentiations. This is why the verifier takes linear time. It has to do these two linear size exponentiations plus some combination, some logarithmic number of exponentiations. This part is kind of irrelevant. It's only logarithmic work. This is where all the work is. Okay? Because this is two linear multi-exponentiations. But it turns out these are fixed generators. Like Hugo was asking, these generators G and H are actually fixed once and for all, forever, which means that first of all, we can speed this up using pre-computation. That if you have to do fixed generator exponentiation, you can massively speed it up. And we can also, if we have multiple proofs to verify, as we'll see in a minute, we can verify all of them together very quickly just by combining these relations. Yeah, so we'll see how that works in just a minute. Okay, good. So how do we put this to use? I'm almost done. Let's go back to range proofs. So this is our range proof. Basically, what we're going to do is, this is the bit decomposition, beta, our bit decomposition. We're going to look at the vector beta minus 1. Yeah, we're going to subtract 1 from everything because we need to compute beta 0 times beta 0 minus 1. And what the prover will do is he will send the commitment, a multi-commitment to the beta L and beta R. In the classical schemes, that commitment would be linear size because we have to commit to every bit individually. Here, with a single group element, we commit to all the bits at once.
You said it's not zero knowledge because there's all this auxiliary stuff that you have to send.
That's right. This is not zero knowledge. We're not done yet. That's very important. So far, I'm blinding this. So this part is zero knowledge. This is just a random group element. So that's easy to simulate. Yeah, I blind these bits. And now it turns out, now what I have to do is prove that this is a bit decomposition, and that all the values are actually, and that this is really all the bits are really 0, 1. Okay, so that's what we have to prove. And again, this part I have to say is kind of mechanical. I'm not actually going to show you. This is like it's kind of what is it called? The kind of cliche in this area that once you have a sound system, adding zero knowledge is actually quite easy. We just have to add blinding factors. So really all we do is we're going to mask these beta L and beta R vectors and then commit to the masks. Yeah, so it turns out that's what makes it zero knowledge. And of course, we combine all the equalities into one using the methods that we saw at the beginning. And that's all I'm going to say about that. Yeah, so the core of the proof was the inner product argument. Once you have the inner product argument, everything else is kind of mechanical. So sorry, but that's all I'm going to say about that. Okay, so the end result is we get a range proof for n bits, n bit ranges. That's of size 2 log n. So like I said, very, very, very short, 2 log n, compared to linear before. But this gets really interesting, like Muthu was asking, this gets really interesting if we have multiple range proofs. Yeah, so if we have multiple commitments, and we want to prove, so D commitments, and we want to prove that all of them are within a certain range, well, the circuit size is n times D. N times D. We take logarithms of that, and really, this just becomes an additive log D term. So if I have 1,000 range proofs that I want to do, just think about this. This is kind of remarkable. If I need to do 1,000 range proofs, the proof is the same size as a single range proof plus log of 1,000 plus 10 additional group elements. Yeah. So this is kind of, I don't know, it's a little surprising, I think.
What about the verification?
What?
What about the verification?
Verification time is linear. That we can't do anything about. Verification time is linear.
Even in the batch setting.
Even in a batch setting where verification will be linear. Yeah, because you have to derive these vectors, this vector s, to do the multi-exponentiation. Yeah, but the proof size, like if you have 1,000 proofs to do, the proof size only grows by log 1,000 group elements. You add 10 more group elements and you've done 1,000 of them at the same time. So if the witness for all these 1,000 range proofs is held at one party, this one party can generate the full proof. Otherwise, if the range proof itself is going to split, if the committed values are split among parties, we give a simple MPC to actually generate the full proof. So you can even generate it in a distributed fashion. Right? So this is kind of the important property of these schemes. So just to drive this point home, let's look at some graphs. So a single range proof using traditional Sigma protocols takes 4 kilobytes. Using Bulletproofs, a single range proof, this is I think 64-bit range proofs, takes 672 bytes. By the way, I'm comparing it to snarks. So snarks are 188 bytes, but snarks, remember, require trusted setup. Yeah, so not quite in the same model. So the proof is 4 kilobytes versus 672 bytes. If I need to do 2 proofs, the traditional methods grow linearly. Our methods only grow by a few elements. Yeah, so it becomes 700 elements. And then if you need to do like 10 proofs, again, the traditional methods grow linearly, whereas we grow, very, very, very little. All right, so that's kind of just to show you how these things grow. And then maybe in the interest of time, I'll skip this. I'll just say that, in fact, there's ways to batch verify. So you can verify many proofs together at the same time. So
Dan, would you have the CT? Could you go back to the
this one?
Where's the CT? Where's the CT thing?
Oh, this is the Sigma protocol. So the Sigma protocol is, traditional Sigma protocols are quite large. They're linear. This is basically a linear line. Whereas this line that you can't see is the logarithmic line. So it looks like a straight line. Yeah, okay. So you can see these proofs are about a kilobyte long. I'm going to skip this. You can verify a lot of them together quickly, just in the interest of time. And finally, I'll say that even if you look at beyond range proofs, if you look at arbitrary circuits, again, snarks are always constant size. Snarks are always 188 bytes, but need trusted setup. These proofs, again, you can see they don't grow very much, right? This is a logarithm line. So they remain, even for, what is it, this crazy number of gates, they're only like 2 kilobytes. Okay, this line is probably out of date, so I'm not going to say anything. Yeah. Okay, good. So that's the point of that. And so yeah, so you can see even for like practical circuits, the proofs are like 1,300 bytes, not too big. But of course, they take a long time to verify. Yeah. So verification is linear, so they're actually quite slower than Snark. So there's a cost to not having trusted setup. Okay, I'm basically done. Basically done. Okay, so one of the cool things, by the way, in working on blockchains and kind of the technology for blockchains is they do cool stuff. So I guess you kind of declare success for your work when actually somebody actually puts it on a T-shirt. Yeah. So this is actually the actual protocol on a T-shirt. I'm not wearing it today, but it's kind of a cool T-shirt too, good material. So it's kind of a good thing to wear to the gym.
People go with silver and now with bullet. Oh,
there you go. Yeah, right. So I've worn this to the gym a couple of times, and nobody asked me what the heck this thing is. So I was kind of disappointed. All right, and so just to summarize, basically, this is a great time to be doing crypto. Lots of very deep work that's like 30 years old is actually being deployed and protecting lots of money. So it's kind of cool to be working in this area. Some interesting open questions, like none of what I told you is post-quantum secure. So can we have a version that is post-quantum secure? Jonathan has been doing a lot of work on that, but the proofs are much longer than what I showed you. So this is a really interesting open problem. And then we don't really have a reason to believe that log n is the best we can do for range proofs. Maybe we can have even shorter range proofs, and that would be really useful. the folks in Monero and Grin and all these other projects would use that right away. So if you have ideas for how to do shorter range proofs, this is of like immediate practical value. So that would be quite influential. So I encourage you to actually try to think of even better range proofs than what we have. But for these projects, it's absolutely vital that there's no trusted setup. Yeah, they don't want to do a trusted setup. So the question is, can we beat it with no trusted setup? All right, awesome. So, sorry, one last thing is I have to advertise. I'll go into advertising mode and then I'll stop. So in February, we're running our, our blockchain conference. The call for papers is out at this site, SBC20. Submit talk proposals, and yeah, please come. So please submit. And it's a technical conference on blockchain, so we'd love to see everybody there. And I will stop here. So thank you very much. Not too late. We'll stop.
You can just take more questions offline. We should let people go if they want to. Tomorrow we're going to shift gears and start discussing Byzantine agreement.